So the handouts you've been given, and again, I'll probably update those with that other handout. But basically, these have all the formulas you'll need. Now, I'm not sure if the formulas might not. Yeah, they don't actually give you the formulas for the moment of inertia and such. So we'll have to keep this sheet going, okay? And we'll talk about what all these mean. But this shows you the different shapes. And that kind of gets into what we're going to be looking at. That's like an unevenly distributed load, isn't it? And then here's some more. It gives you the area, X bar and Y bar.
Your screen's on. Yeah.
Oh, I'm sorry. Well, you see it on the video. So we'll start that over again here when it comes up. You have to know the moment of inertia because that's going to help you when we start applying forces on different shapes. And the moment of inertia then, and it's kind of a screwy unit. It's either inches to the fourth or meters to the fourth or something like that. To the fourth, yeah. It's like, how do you we know the 3 dimensions, right? Where you've got squared would be like an area and cubed would be a volume, and then we've got the fourth. So that's kind of a departure from normal, but we'll just deal with that.
But this is still 2-dimensional.
Yeah, we're only going to be dealing with 2-dimensional. So in all these different shapes. Okay. Now, and I probably will show you how we can do that using the CAD system, because we can do that just with simple AutoCAD type moves. We can draw that shape and make a region out of it, and then go and find the engineering data on it and be able to find out what the moment of inertia is, the centroids, and so on. So radius of gyration, all kinds of different stuff. So basically these are the calculations for that. And this sheet will be dealing, you first have to find the center of gravity, then you use that to help calculate the moment of inertia. Okay, so we have to find that point where these different shapes would, if you stuck a pin through there, and it would just spin freely and be, if you will, balanced. Okay, so that's what you're looking at when you're looking at the center of gravity or the centroid. This page will be how we'll calculate all those. So we're looking at the area, base times the height for a rectangle, triangle, base times the height cubed, circle, pi d squared over 4, and semicircle, and so on. Okay? Now, then, what is X bar and Y bar? Well, X bar and Y bar are those locations from the respective axes that tell you where that point is. So the X bar will always be measured off of the y-axis. Okay, it's how far from the y-axis you go over to that point. That's X bar, and that's what it's called, X bar. Y bar is just the opposite. It's how far from the x-axis are you going to measure up to get that location, up or down or wherever. Also note that when we start doing composites, okay, and we do composites in moment of inertia calculations, the center of gravity does not have to be on the part. So that's kind of tricky too. It doesn't have to be located right on the part at all. So if that, that might look kind of funky sometime, but that's just how it is. Okay. So center of gravity calculations on that 3rd page. And this sheet, I think actually I got this when I was in your spot in 1984 and kept it. See, I told you I kept all my notes. I kept this, and I can still use it because this makes it very simple. Okay? So I have to give credit to Don Young Peter. He was the guy that drew this up. I'm sure he probably used it from somebody else, but he's the one that made this available for me. So it does the center of gravity and the moment of inertia calculations. I think Chapter 7 is strictly center of gravity, so we'll deal with that. But note it's got a description here, y, distance from the base to the center of each area in question. So this is a composite part. So what we're doing here is this I-beam, if you will, and that's not an uncommon shape per se. We split this up into 3 different segments. Let's see, is there a way I could get some of that out of there? I don't guess there is. But we split that up into 3 different segments, and we have to find the center of gravity for each one of those segments. So you can see here, this top box, if you will, is the section he's calling 1. Then this middle section here, section 2, and finally section 3. Well, to find the y-bar, and y-bar is the most common. You don't typically have to worry too much about x-bar, but we can still find it. To find y-bar, we have to take and do the summation, and I think, yeah, here, the summation of all the areas, and then the y distance for each one, divided by the summation of the areas. And you can see here, the area for 1 is 40 square inches. That's 10 times 4, right? Base times the height. The area for the second one, 32, which is, what, 4 times 8, base times the height. And the area of 3, 112, which is 16 times 7. So that's, and he's showing that right here. Then you've got the y-bar for each one of these. Well, and keep in mind, we'll have to make note of where the y-axis is located. Okay, and in this case, it's located on the bottom. So you have to go in and find the centroid for this, or the center of gravity, just for this box. Well, to do that, you would go halfway up the box. It's the height divided by 4, or excuse me, divided by 2, right? So half of that is 2. But then you have to go in and add the rest of it. So 2 plus 8 is 10, right? Plus 7 is 17. Thus, the y for the square of 1 is 17. So it's this distance plus that distance plus half of this. Make sense?
That's the y-bar?
That's the y-bar for... It's like a composite. It's just a y. It's not really y-bar. Y-bar will be the whole thing. Y-bar will be the distance to here. Okay? So it's just the y for that area. Okay, it's the distance from here halfway up. Plus 8 plus 7. Okay?
Why are you doing the total on 2 of them and then halfway on the third? I'm not following.
You're finding where the center of gravity for this particular block is relative to the y-axis.
Okay, and you know that your y-axis is...
Right. It's just like you could ignore the fact that this block and this block is here. What would the center of gravity be for this piece if it were suspended that far from that axis?
So the bottom of the piece.
Yeah, because you can say the x-axis can be anywhere.
Okay.
Now, typically, we make it at the bottom of the piece, of the overall, the whole composite, right? That's typical. But you can make it anywhere you want it, as long as you tell them how far it is away from something in that composite.
So if something was suspended, then that x-axis would be at the top
Yeah,
instead of the bottom.
it could very well be. Okay? So that's why it's, yeah, you add those 2 up plus half of this one. Just like on the second one, you would go to this point right here, which would be half of the 8 inches, right? So 4 plus 7 gives you 11. Then the third one, you're only going to take half of this 7 here, because this is the axis that we're trying to measure relative to. Okay? So you've got the area of the first block times the center of gravity of the first block. The area of the plus the area of the second block times the center of gravity for the second block, plus the area of the third block times the y for that particular area. All divided by all three areas. The only exception to this, and that gives you the y bar, which is this means that it's 7.74 from the base up to this point right here. Okay? Now you could do the same thing for x bar and take the area of that first block, which would be the same, times the x for this distance right here, which would be 5, right? Plus the distance from here to here, which, let's see, this one's 16 and this one's 10. So that distance would be 3 inches, wouldn't it? If it's, in fact, centered, and we think it is. Then you would take this distance, which is 2 inches, plus what? If it's 4 and this one is 16, that leaves you with 12, so another 6 inches. So that would be 8 inches, wouldn't it? Then you would take the third one, which would be half of the 16, which would be 8. Is there a common theme there? They all ended up 8, didn't they? Guess what the ultimate number is going to be for that? 8. As long as everything's centered up, the x bar is going to be 8. You could do the all the areas and then divide by the areas, and it's still going to be 8. Okay, unless this thing were offset some way. If it were offset an inch, that's not going to be 8 anymore. Okay.
You get 8 inches from the y-axis, which is going to be on the left side of the part.
That's correct. Or it would even be on the right side of the part. It's still, either way, it's going to be 8 inches in that case.
I don't see an x or a y-axis on the drawing.
Right, and that will be spelled out for you on the problems I give you, on the problems that I make up. Now, the ones in the book, I don't remember if they are or not. And they give you the x reference axis on all of them, and then some of them that need it, they give you the y axis. Yeah. So that'll be spelled out, and you just measure from there. Okay. It also, on that first sheet, it does show you a reference to that. See how this triangle is referenced to the x and the y axis, and the rectangle is referenced to the x and y. So that's typical of what we would do. Okay? So we measure up and we measure over. Again, y bar is going to be relative to the x-axis because it's a y distance, isn't it? Okay? And the x bar would be relative to the y-axis. If you read that in the book, that's what they're telling you. Okay, so we do that, and that tells us the y bar. And actually, Chapter 7 is just that, I believe. I think that's the centroids and center of gravity. That is what's going on. Chapter 8 is moment of inertia, which is the bottom half of that. So,
is centroid and center of gravity like two interchangeable terms, or is it
pretty much? And I was going to look for something in here on the difference. What they say. Says the resultant, let's see. Force system may be categorized as a parallel force system, and algebraically, sum, which is the resultant of the system, is called the weight of the body. The resultant of these individual gravity forces will always act through a definite point, regardless of how the body is oriented. The point is called the center of gravity. So that does its thing. Now, as far as centroid, let's see, or if they talk about the centroids. Centroids on page 145. If we assume that an irregular shaped flat plate shown in this figure is homogeneous and has uniform thickness, okay, and that has to be. Homogeneous means it's just got the same properties, if you will. And uniform thickness, in other words, the density is the same. The weight of the plate would be directly proportional to the area. Thus, we can use areas instead of weights. in the equation in section 7.2 to determine the location of the centroid of the area. This strategy is equivalent to allowing the thickness of the plate to approach zero and finding its center of gravity. So centroid, thickness, weight, if you will, center of gravity, just a skin, if you will. Okay? But you're finding the same thing. You're using the same techniques. Everything's the same. Okay? So I kind of use it interchangeably. So that gives me Y bar. Now, that's as hard as it gets for that. It's just, now, I guess there is one other thing that can make that a little bit more difficult. If, for some reason, we have a hole in this piece, okay, we've got a hole in this piece, we would have to have a fourth object, if you will. We'd have to have a fourth object, and so we would have a fourth set of numbers here, right? And we would have to subtract. When you cut a hole in something, you have to subtract that area. Whether it's a hole or a square or whatever, when you remove something out of that shape, it has to be a negative value. That's the only difference in this setup here. Okay?
The denominator would still be the same, or would you subtract on the top
Well,
and the bottom?
you subtract top. You have to subtract the area. The area in this case, let's see if we can, if we've got one here handy. Actually, they do example 7.3 on page 146. So let's just let's pull that up and do it if we can. Why not?
7.3.